Swayam Prabha. Digital India. Educated India.
Okay, so let me give you a geometric interpretation to this duality. Okay, so consider I have a set M, which is a subset of Rm plus 1, and M, of course, is number of inequality constraints. Okay, just keep that in mind. Okay, the x-axis in all these figures would sort of represent Rm in a concise manner. So just be careful here. All points on the positive x-axis, they would sort of characterize points which are whose m coordinates are all positive. Any point here would characterize a point, right, whose all m coordinates may not be positive. If this is confusing, you can just assume m equal to 1 and go ahead, right? There is no problem in doing that. So once again, consider this set M as shown in this picture, this entire shaded area. Okay, I want to find the point, right? Or basically I want to find the y coordinate of the point which is in set M but is also lying on the y-axis. Okay, once again, I want to find the y coordinate of the point which belongs to this set M and also to the y-axis. Okay, so you can see here M intersection the y-axis, and I want to find the infimum of the y coordinate. So what is that going to be? It's shown in this picture. It's P star, right? This number. Here?
Yes, sir.
Okay, it should be. Yeah, okay. So this is one thing. Okay, and I'm going to denote this by P star. I've used the same notation for deliberate reasons. We'll see why I've used P star. Remember, P star was also the primary problem. Okay, next. This is where it may turn out to be challenging, but let me try. So consider a non-vertical hyperplane. You understand what? So if this hyperplane is confusing you, think of it as a line in R2 by assuming that M is 1. So consider a non-vertical line in R2. Non-vertical and vertical, what would be the difference? I take this is my vertical line. What would be the normal vector to this line be? Anyone?
It'll be X, sir.
X, comma. So if I write the y coordinate of this normal vector, that would be 0. Right. So as far as I have a non-vertical hyperplane, right, I can always, so if I have a vector x and y, which is representing, say, normal to a particular line, right? Nx or let's say px comma py, that also would represent normal to the same plane or same line. Right? By scaling a vector, it still remains a normal vector, isn't it? It may not remain a unit vector, that's fine, but it is still going to remain normal to the same plane or line. Agreed?
Yes, sir.
So then by choosing an appropriate t, any non-vertical hyperplane, I can write it normal as this, mu comma 1. Right? By finding t such that ty equals 0, 1. As far as y is not 0, which it is not, since I'm only using non-vertical hyperplane, there always exists a t such that ty becomes 1, and therefore the normal can always be written as mu comma 1. Okay, now the question is, let's say so just giving you the normal vector doesn't give you the exact plane or line, right? This plane, which is parallel to this plane, will also have the same normal vector. Question now is, this normal vector, right? If this hyperplane passes through a particular point, let's call it x1, w1, which is an element of this set M, then I'm specifying a hyperplane, right? Then I'm uniquely saying which hyperplane I'm talking about. Just giving the normal is not enough. Also telling you that this plane passes through this point. Question is, what is the intercept? Right? All of you, I'm sure, understand intercept. At what y coordinate does this line, if you want to think of it as a line, intersect? Anyone? Of course, the answer is there on the slide, but see. It would have to be mu transpose x1 plus w. And if you are thinking of the case where m is 1, it would be just mu x1 plus w. Okay, that would be the intercept value c. Next, still not done. Now, for all the hyperplanes which have the same normal vector mu comma 1, what is the smallest intercept that you can get such that the hyperplane still passes through the set M? And so if I compare this figure, the intercept value is this. Can I use the same hyperplane? By same hyperplane, I mean the same normal, but I can shift the hyperplane so that this intercept value is reduced. So of course, if I shift this in this direction, you can clearly see this value will come down. What is the least I can get? That is pictorially or graphically represented here. That intercept, I'm going to, since it's a function of the normal, right? I'm not changing the normal vector mu. That function I can represent it as q mu, that value. That is my q mu. And I can write this q mu as infimum over all xw's in my set M of this mu transpose x plus w. Right. Think about this. I'll be back in 2 minutes.
Sir, could you go back to the previous slides for a moment?
Okay.
Sir, the previous ones to this, and the previous one to this, and the previous ones to this.
This.
Yes, sir. So,
Okay. Hold your question. Think about it. I'll be back in 2 minutes. This is not a break. I'll be back in 2 minutes. Definition of q mu clear. In this picture, I'm not allowing you to change the hyperplane normal. That's fixed to the vector mu1. But I give you the freedom to slide the hyperplane as much as you want. The only condition is that the hyperplane should intersect with at least one point in this set M. Then why should you slide this plane? Because you would want to minimize this intercept value. Make sense or no? I mean, please don't try to think of how this is related to the optimization problem as now. This problem in geometry itself, I hope, is clear.
Yes, sir. Clear.
Now, what would be the next step? I have till now not allowed you to change the normal vector mu comma 1. Right? Let me also allow that freedom. But this time the freedom is there not to minimize. You should use the freedom not to minimize the intercept, but to maximize this minimum intercept. So I would want you to choose a normal vector mu such that the least intercept is maximized. Okay. D star is the maximum intercept by allowing you to choose any normal vector. The only condition is it cannot be a vertical hyperplane. Okay, which is why the variable is only mu, not mu comma t or whatever. That maximum intercept is what I am calling D star. Okay. In this geometric problem, what is the relation between D star and P star? Anyone? So, Himika, you seem to have raised your hand. Is there any question you have?
No, sir. It was during the time
Okay,
you asked the poll.
That's fine. So D star and P star, should they be different?
They seem to be equal in this particular case.
Great. Right. So in this case, they are equal. Are they always equal? No. If I take a set that looks like this,
Okay, so
P
if it's a
star-
convex set, then it will be equal.
great, thank you. So I hope you see why convexity is important again. If M is convex, although it's not a proof, but I hope you can intuitively convince yourself that D star and P star will be the same. Okay? So now the question is, how is this related to optimization, right? Let's bring it back to where we started. So remember, the optimization problem was, if we write it, maybe forgotten it already. X is in X such that Gx is less than 0. Okay? I'm going to represent the value of this function Gx, right, at any x is in Rm, right? So these m numbers are going to be geometrically represented on the x-axis, whereas the objective function is just one number that I'm going to represent as the y-coordinate in the picture. So then let us take m bar, right? M bar is the set of all tuples gx comma fx for all feasible points. If once again Rm is confusing you, you can think of M as 1. So only one inequality constraint. Alright? Does M bar make sense? The x coordinate is the value of some x. In x, the value is gx. Okay? So the x coordinate in this picture does not represent x, it represents gx. Right? And similarly, the y coordinate in this picture does not represent x, it represents the value of the objective function at the same x. Right? And in general, of course, gx can have both negative values as well as positive values. Okay? So for the x's for which gx is negative is this side, the x's for which gx is positive is on this side. Okay, now that's not enough. So this M bar is shown over here as this gray area. On M bar, what I'm going to do is get a different set M. How is this set M defined? If you look at this, it consists of points x, comma w in Rm plus 1. So points shown over here, such that there is some element u in my set x where the inequality function gu is less than x, this x. right? And when I say one vector is less than equal to other vector, what do I mean? This is entry wise. Okay, so all m elements of this vector are less than all m elements of the right hand side. So let's take this point over here, x comma w. How do I find if this point x comma w is in the set M or not? Does there exist a u in x such that the value gu is strictly less than x? That means gu should be on the left hand side of x. If I take this point, is there a point in my set x whose inequality functions have a value less than this x coordinate? Is there a point? Anyone? So if I take this point, where does this point come from? Comes from this set, right? What is the x coordinate value at this point? Is gx. Is gx less than this x?
Yes, sir.
It is. So therefore, the first condition is satisfied. How about the second condition? The y coordinate of this is fx. Right? Is w greater than fx? Is the y coordinate of this point greater than this? It is. So therefore, it satisfies this condition as well. Therefore, this point is included in my set M. How do you visualize it? It's basically like if I have a point in my set M bar, all points to the right of this point will be in M. Similarly, all points in the straight line, vertical line above this point will be in M. And all points in this is it called quadrant, will also be in the set M. Okay, so that I hope is true. I hope you can understand this. So if this is my M bar, you can see there is this blue area that I had painted. That this blue region is not in M bar, but it is in M. Why? Because if I take a look at this point, as I said, to construct M, I have to include all points to the right, all points above, and all points here. So that is why this blue region gets added to M bar. Is that okay?
Yes, sir.
But please repeat what is M bar. Why it is not in M.
So M bar is this set, right? So you take all elements x from your set x. Right? This x could be Rn or some smaller set. Now on this x, for each element of this capital X, you evaluate the inequality constraints and you evaluate the objective function. The inequality constraint value will give you the x coordinate and the objective function value will give you the y coordinate. Make sense?
Okay, sir. Okay.
Gx interpret it as x coordinate, fx interpret it as the y coordinate. Right? For every x in the capital X set. That is how you get this gray shaded set M bar. From M bar, you basically take all points one by one. This is the point. Include all points to the right of this point and include all points above it and all points in this quadrant. All these points will be included in M, which is why I've drawn all these vertical and horizontal lines. Okay, so that is how we will define this set M. Now again the same question. What is the P star for this set M and what is the D star for this set M? That is the question. First of all, let's look at D star. D star, I will just redefine it here. It is the supremum of Q mu, right? Over all mu's, by the way. I can go back to that slide and show. As of now, I'm not putting any restriction on mu. Mu can be any number, any m tuple. Now, when I choose this particular set m bar, what happens if mu is not positive? The answer is there. Anyone? What happens if mu is not positive? The answer. Wait for some of you to take. See, mu is positive. All hyperplanes with normal mu comma 1 would sort of point. The normal would be in this direction, right? As I said, positive x-axis means mu is positive. Negative x-axis means mu is negative. So, can I take this as a hyperplane? This also has normal mu comma 1, right? You see the y-coordinate of this normal is positive. But the mu, the x-coordinate is negative. What would be q mu for such a mu given this set? When will I, or what is the smallest intercept that I will get for this hyperplane? Remember, q mu is this, right? It's in a, it's in m x plus mu transpose gx, right? Or in terms of the set M, geometrically, what does this mean? X comma W in M, mu transpose X plus W, right? But now this set M, it extends right up to infinity on the right hand side and plus infinity above. All of these are points in my set M. I take this hyperplane, what will be the smallest intercept I will get? Even with this hyperplane, if I put it at this location, this is my intercept. But I want the least intercept. So what? How will I get the least intercept? By sliding it to the right, isn't it? How far can I slide it to the right?
It is unbounded. It will go on and on.
Exactly. This will be
It
minus
doesn't
infinity.
make sense. Okay. Sorry. I thought we were trying to like go towards the shape. So just why I was thinking, why is this question being asked?
Because now your set is not m bar, it's this m, right? This huge m.
Okay. Right.
So a value of mu which is not positive, or sorry, not or is negative, right? Q mu has to be minus infinity.
Yes. So yeah, I think we established that earlier. No? As in
Exactly. So
same.
that was looking at the optimization problem. Now you have a geometric picture,
Okay. Good.
right? So Q mu is going to be negative as far as mu is. You allow mu to have negative values. So that's one thing done. What is P star? How can I write P star? P star is the smallest intercept of all points on M as well as on the y-axis, right? So that was the definition we gave here. What are the points? What are the kind of points in our new set M? They are nothing but the x coordinate is 0. What does that mean? X coordinate means gx, isn't it? Y-axis means x coordinate is 0. X coordinate, as I just said, is nothing but the value of gx. That has to be 0. But is that true? What is the difference between M bar and M? If I have this point, right, then this point is in my M, but this point is not in M bar. And when will this point be included in M? If there is some point in M bar to the left of it. Which means I'm just comparing the x coordinate. Therefore, there has to be some, if I'm looking at x coordinate being 0, that means there has to be some gx which is less than equal to 0. And of course, w is nothing but the y coordinate. Y coordinate is nothing but the objective function. So that's fx. Okay, so this finding this p star is nothing but this problem, and this problem is the primal problem. Similarly, what is d star? So what is q mu? And q mu is, anyone who's still awake? Anyone wants to specify what is q mu? It's for w in m of mu transpose x plus w. But what is x in this particular m? X is nothing but gx. W is nothing but fx. Therefore, q mu becomes infimum over all x is in x, such that fx in infimum of fx plus mu transpose gx, that is nothing but your Lagrangian. So all I'm trying to say is this q mu is not affected by whether you are taking q mu of m or m bar, right? Because q mu is always obtained by shifting hyperplanes to the left and bottom, whereas the difference between m bar and m is always towards the right and to the top and in this order. So q mu for m and q mu for m bar would be the same as far as your mu is positive or at least non-negative. So that is what will give you this. And then you're supposed to maximize this q mu for all positive or at least non-negative mu's. So that is your dual problem. Right? And you can see clearly that in some cases, as this m bar, your d star may be strictly less than d star. Okay, so now I think it makes sense. So here is another example of m bar. Is m bar a convex set?
No, sir. No, sir.
It's not. But what about the set M? This entire thing. This
Sir.
is convex.
Yes, sir.
Okay, so in this case, you can see d star and p star are equal. So strong duality may hold even if m bar is not convex. Main thing is we need to worry about the bottom part of m bar. How is that? If that looks fine, then your strong duality will hold irrespective of what happens on the top. So I will not prove this, I'll just give you one set of conditions that if my objective functions and inequality constraints satisfied, then strong duality is guaranteed. Okay, so that is theorem and it's called convex programming duality. Says that as far as p star, right, you should always think of this as p star. As far as p star is finite, okay, because you may also have a set m or m bar that sort of looks like this, everything below this. Okay, in that case, You can see the smallest y coordinate on the y-axis is negative infinity. Okay, or I can take another set like this. There is no intersection at all with the y-axis. So this infimum does not exist or is positive infinite. As far as this P star is finite and that there exists an x such that gx is strictly negative. Why? As far as there is something on the left hand side, you can see that I will always have this thing, this point to be finite. If there is this set, if this is my M, right? What would Q mu be? Or if there is only, let's say, one point here, something like this, just this line and then something like this. Q mu would be for a vertical hyperplane, right? So mu will not exist. So what this says is, if P star is finite and there exists an x such that gx is strictly less than 0, then strong duality holds. And also there is a mu, right, which maximizes Q mu. I hope that sort of, I know I have not proved this, I'm just hoping that this geometric picture gives you enough intuition to understand these statements. Because once this strong duality is guaranteed, then you can go ahead and solve the optimization problem by solving the dual problem, which is stated over here. One of the most primitive algorithms that is used is called dual ascent. What it does is, you can see instead of one constrained optimization problem, I now have two almost unconstrained optimization problems. Almost because there is a small constraint on mu that it has to be non-negative. But apart from that, I have removed all constraints, right? And I have two unconstrained optimization problems. So usually what one can do is you can start with an initial estimate for both the primal variable x, dual variable mu. Then you can sort of iterate over both these optimization problems. So first you can try and solve the minimization problem for a particular value of mu, which is k. Once you have obtained better estimate for x, then you can plug in that and then solve for mu. Okay, now the thing is, mu, this maximization is a maximization of a linear function. So in principle, there is no maxima, but we can do a gradient ascent step, okay, instead of a gradient descent. You want to maximize this. So the gradient of this function with respect to mu is just g. And of course, you want to ensure that mu is non-negative. So this particular step over here is just your gradient ascent. Then you are just doing a projection basically. So if this gives you a negative, then you do not want to accept it. You would rather accept that mu. So this is how you can iterate and then hopefully converge. Of course, this is a very primitive method in the sense its convergence speed and all that are not very good. So there are several modifications and variations of this. One of it is called penalty method, the other is called augmented Lagrangian method. Hopefully some of you have heard of it. This is also sometimes called as alternating directions multiplier method. In short, ADMM. Okay, so that is basically what I wanted to tell you about convex optimization. There are several theorems for strong duality. So one set of conditions is convexity, as I've stated here. But strong duality can hold for several other conditions also. Okay, so this is not the only condition, and of course, given the time, I will not go into several other conditions. But you can sort of, if you are interested and if I have not tortured you enough, and look at some of these references. This geometric interpretation of the primal and dual problem that I presented is basically taken from this book, Convex Optimization Theory by Perseus. So, wonderful book. It's wonderful if you like math. It's an out and out math book. For several pages, you may not even see what is the relation with optimization, but later on, it's just magnificent. So I think I will stop here. I have sort of overshot my time limit by a large amount, 45 minutes. What I will do is, during the lunch, I will upload the lab handout. Okay, you can try it yourself. Instead of starting at 2, maybe we'll start at 2:30. Okay, I'll also upload the slides, the entire slides. Remember, there is this linear algebra section that I have not gone through. I think there's not enough time for that. During the lab, in case you have doubts, you can ask and we'll discuss the linear algebra portion as well. But for now, we'll break for lunch. We'll meet at 2:30, same link. Okay, the lab handout will be available to you in about 10-15 minutes. Thank you. Once again, apologies for taking up your lunch time. Hopefully, this will not happen tomorrow. Thank you.